right, good evening, everybody. We have a few chairs left in our main room here. If you folks want to push in that way, if not, if you're comfortable, that works for us too. Hello, welcome to episode 97 of the Batavia Lyceum Association, smartest room in town. Hi, everybody. For those of you just joining us for the first time, we have a donation jar here. We like to pay our speakers a little something. We ask for a $5 donation. It's right here. We'd like to thank Melissa and Ryan for opening up their bar to us every Monday night. They're usually closed. They open for us so that we can be smart together. The bar will stay open throughout the presentation. Be sure you drink a lot. I know in my case it works, but I don't know about everybody else. So tonight we have a special treat. Super excited. Dr. Lincoln will be talking about women in science, or mostly science, I hear.
Yes.
She's a known quantity, a writer, a teacher, all-around Renaissance woman, and we're super excited for this presentation. So a warm round of applause.
Thank you for that very kind introduction, and thank you to the Lyceum for hosting us. I'm excited to be here. Tonight, I'm going to tell you about remarkable women in science history. I am, as he said, an author and a former teacher. The book I wrote is about scientists. Let's see. Okay. That's the book I wrote, and it has some of the stories you'll hear tonight, but also it has stories about men like Walter Alvarez, who discovered that a meteor killed the dinosaurs, and Mario Molina, who saved the ozone, Dr. Hale Williams, Dr. Daniel Hale Williams, the black surgeon who performed the first heart surgery in the United States. So those guys are in the book too. If you like tonight's presentation, I'd like to invite you now to Pachakacha night, where I will take 6 minutes to tell the story of how my book, Science Discovery Files, began in my classroom and ended up on the library shelves. So Pachakacha is 20 slides, 20 seconds each, and there are about 10 of us who do a little 6-minute presentation. So mark your calendars for that too. Pachakacha. It means chit-chat in Japanese. So, all right. So the 5 remarkable women I'm going to tell you about tonight pushed our knowledge of science forward despite laws that prohibited them. Now, there's a lot of women in science. I chose not to include Barbara McClintock, even though she pushed our knowledge of genetics forward with her study of corn. And I decided not to include her because there were no laws that prohibited her from doing science. I also chose not to do Tu Yao Yao, who was the first Chinese woman to win a Nobel Prize for discovering a cure for malaria. Chose not to do her because she didn't only have laws that prohibited her, quite the opposite. The Chinese government encouraged her to find a cure while they kept an eye on her family. But the women I'm going to tell you about tonight are, you'll see. I chose 5. At the end of the discussion, we might talk about how strong and brave the people were who supported them, their cool science discoveries, or what we can do to spread the word about Eunice Split's contribution. The first one I want to tell you about is Florence Nightingale. Now, we all know the name, and we all know that she was a nurse, but few people associate her as being a scientist, and yet she was. She was very wealthy. That's the house where she grew up. She had tutors who taught her languages, because at the time women didn't go to school, but they taught her languages, mathematics, and philosophy. And like you see here, her parents wanted her to marry a wealthy man. They deemed that nursing was unfit for a lady. And at the time, before Florence Nightingale, it really was unfit because nurses were nothing more than entertainment for patients. But she believed that nursing should be more, and she believed that God called her to be a nurse. She educated herself by going to Germany and shadowing a couple of doctors, finding out what they needed, what would make their lives easier. And then she returned to London, where she worked as a nurse in a London hospital during the time of the cholera epidemic. Now, at that time, they knew nothing about germs, and yet people found out that clean water was the key. Now, if you want to know more about that story, you should look up Jon Snow when you get home. Yeah, okay. But they didn't know anything about germs, but they were learning how to prevent the disease. Anyway, when she was working at Middlesex Hospital in London, she read the newspapers along with all the other citizens of London, and she wished that she could help. The Crimean War, just a little brief, is known as the War of the Empires. In the upper right was the Russian Empire, and down here in the lower left was all the Ottoman Empire, and then one day the Russians just decided to attack right there in Moldova, very close to where they are today. And so the French and the British came to the aid of their allies, the Ottoman Empire, and that's what started it. And it was a brutal battle that went on for 3 years. The Crimean War looked very similar to the U.S. Civil War, took place around the same time. There were smoky guns, horses, and cannons. It was also the very first war to be photographed. So, for the very first time in history, families saw what their loved ones were facing away from home on a foreign battlefield. So, like I said, Florence and everybody in London were reading the newspapers, and the London News reported that British soldiers were 4 times more likely to die from disease than from battle wounds. I can only imagine what people would think about that. You're so afraid of war, and yet it was the disease that was killing people. So step it back a minute. I told you Florence Nightingale was very wealthy. She was on a cruise ship one day, and she was talking to this man, Sidney Herbert, and she was telling him her ideas about nursing. And he was the when he became the Secretary of War and the war broke out, of course he thought of Nightingale, and he wrote a letter to her and asked her if she could help. So Nightingale rounded up 38 volunteers that were mostly nuns, women willing to go to the front. Now, no females in Europe had ever been to a war zone before, so this was really radical. But anyway, when Nightingale arrived at Scutari Hospital in Turkey, she found chaos. It was this big, beautiful building with huge corridors, 3 stories tall, and it had a courtyard in the middle. But the courtyard was being used as a garbage dump, and the first floor is where the sick patients would be deposited, and you could hardly get past there. The second and third floor were pretty much wasted because they couldn't get past there. And I know you read those words there, overcrowding. There was cholera too, vomiting and diarrhea. I mean, it's no wonder that people were more likely to die from disease. So anyway, it turned out that Florence was exactly the right person for the job. And you're probably wondering right now, well, what's that got to do with science? We didn't get there yet. Okay, I promise. She could read and write fluently, and she had experience during the epidemics, and she was a natural leader, so she was like the perfect person to be there. She got some volunteers from Turkish women who lived there, and they helped carry fresh water, mopped floors, did laundry, all those things I had listed. If you could imagine, they removed the garbage from the courtyard, and they washed the walls and fixed leaks. And in addition, they helped with the bloody surgeries. Nightingale wrote to the Times of London when they needed bandages and soap, and the citizens responded. Patients very quickly appreciated that there were women at the front. I mean, at first they thought they would be a distraction, but it turned out that they were quite necessary. And this is when Florence Nightingale became known as the Lady with the Lamp. Because each night, after working hard all day, cleaning and mopping and assisting, she would make her rounds and meet all of her patients, and then, this is where the science came in, she went back to her room and she recorded what she saw. How many people died from disease, how many people died of injuries, and so on. And then she put all of this on a graph, where blue represents the deaths by disease, you can see, and red, which kind of looks pink here, is battle wounds, and black is just other undefined. You can see that there were more soldiers killed during the winter. This is the first year. December, January, February. Far more blue than in the summer months. So not only did she keep the data, but she analyzed it. She said, more deaths in the winter. What's the difference between winter and summer? She opened all the windows, and as you can imagine, the patients really protested to that because it was cold. But she opened the windows to get the fresh air in, and she removed the heavy draperies to let the light in. Now, what we know about germs now, it makes absolute sense, okay, to have UV light and fresh air. But she made a big difference. The next year, more people died from disease in the summer than in the winter the following year. So how did she save millions? I started out by saying, she was a nurse who saved millions. The war only lasted 3 years, 1,000 days, so do the math. She'd have to save 1,000 patients every day to just save 1 million. Plural millions would be impossible. But this is what she did. She saved hundreds during the war, but then after the war, she spread the word. She opened the first school of nursing, and she spread the word about fresh air and sunlight to nurses around the world. The third thing she did was to present her graphs to Parliament, and they responded by making changing the laws about sanitation in England and in India. So that saved countless lives as well. She influenced the treatments of soldiers during the American Civil War, or we would have lost more Americans. And her techniques continue to save lives today. So, in my book, that makes her a scientist. She died in August of 1910 from a sickness she acquired during her time in Crimea. Okay, so the next remarkable woman of science I'd like to talk to you about is Henrietta Swan Leavitt. How many of you know her? Ever heard of her? Yeah, my husband's got his hand up. Okay. So, this is not Henrietta's long gone house, okay? And house is gone, but I found this on the internet, and I read a book about Henrietta, and it said that when she was growing up, she and her mother would climb out the windows and sit on the roof and look at the stars. So I thought, this house is around the same, it's in Lancaster, and it's around the same time in history, so that's what I imagine her house looked like. But she always wished, as she looked up at the stars, she wished she could tell whether stars were really, really far away and incredibly huge, or if they were relatively close and smaller, because you can't tell, She attended Harvard School for Women, and then there she took only one astronomy class, and she learned that the problem of telling whether stars are far away or close was already partially solved by using parallax. Do you know what that is? Yeah, I know my husband knows that too. Okay, well this is how it works, okay? You can try it. Put your finger out in front of your face and line your finger up with something that's vertical in the room. Just leave it there, right?
close one eye and look at your finger. Now without moving your finger, look at the other eye. And it jumps. Yes, it jumps. Okay. Now, do the same thing, but put your finger close to your face. One eye, and then the other. You see that your finger jumps much more when it's close to your face. So what's that got to do with stars? Well, let me tell you. All right. Your brain compares the images from one eye and the other. And if the images are really different, then your brain knows that something's close to you. And if they're pretty similar, then your brain knows that it's far away. So that's how it works. And that's very similar to looking at stars at different times of the year. So let's say in the summertime, you look at this close star. And then 6 months later in the winter, you're about 200 million miles away in a different part of the sky, and you look at that same star, and they're very different backgrounds behind that star. Whereas a far star, you look at it in the summer, and then in the winter, you see some overlap. Okay, so that's how you can tell how far away the stars are. A close star has a very different background at different locations. And far stars have similar backgrounds. The difference, combined with a little bit of geometry, tells you the distance of the star. But parallax, too, is limited. Most stars are so far away that the background is the same no matter where you go. But at least the problem of whether a star was big and far away or close and smaller was partially solved. In 1892, Henrietta Swan Leavitt got a job as a computer, and we all know that before computers, we're human beings, and she worked in the astronomy department at Harvard. Well, because she was female, she was not allowed to look through the telescope. Yeah, go figure. I don't know what she was going to do to that telescope, but yeah, she wasn't allowed because she was female. But actually, Henrietta was pretty happy because she was one of very few women who actually even had a job. In addition to computing, Leavitt had to record the brightness of stars. So on the right there, you see an actual plate, which is a photograph on glass. The dark dots are stars. It was before electricity, so she would put the glass plate on this light box that had a mirror underneath that would grab the light from the room or from the sun, and then she could see those stars. And then she would label their sizes. And these are the tools she used. Besides her light box, she had, of course, a handheld magnifying glass, and I included this because I just love this second thing. They call them fly spankers because they look like tiny little fly swatters. But what it is, they were little homemade gauges, just a piece of glass that they put a wire handle on, and they wrapped it with adhesive. But they would use those fly spankers to determine the size of the stars they were looking at on the glass plates. And of course, she had an extra magnifying glass just in case. Some of the images Leavitt studied were taken in Lima, Peru. Few people in New England even knew that the small Magellanic Cloud existed. We can't see it from here, of course, because it's on the other side of the Earth. It's under us all the time. So, and it's called the Magellanic Cloud because when Magellan circumnavigated the globe, he used those clouds for navigation because he could no longer see the North Star. Okay, so I don't know how she did this. I mean, what a tedious task to look at those stars and just try to decide how big they are. But then it was even worse than that. She had to look at the same stars over and over. because she was looking for what we call Cepheid variable stars, which means that they change their brightness. Man, it just sounds mind-boggling to me to have to look at those and then look at them again and see if they still are the same as the last time you looked at them. But anyway, Miss Levitt recorded the brightness of tens of thousands of stars, and she identified 1,777 Cepheid variable stars in the southern hemisphere. Somebody quipped that she found more stars than they have in Hollywood. She noted, as she was looking at all of these, she noted that there might be a relationship between the brightness of the stars and how long it takes them to change, to go from really bright to dull, or duller, bright again. She thought there might be a relationship. So she went to her boss and she asked him permission to look to see if the suspected relationship was real. Now this guy, he's one of my heroes because, he hired her to identify stars, not to go off and do some research. But he said, yeah, sure, do it. And he continued to pay her. But what she was looking at, as you see the brightness, this could be a really bright star. It takes some time to go to bright, down to dim, and back to bright again. Whereas a star that's not so bright would look more like this. Okay, it would take a lot less time, each time it went through its cycle. So anyway, she was a scientist. She controlled her variables. She chose 25 stars in the Small Magellanic Cloud, and the reason she chose them was, twofold. One, the photos were always taken by the same astrograph, the same camera, so she didn't have to make any comparisons, any changes. And the stars were approximately the same distance from the Earth, because they're all gathered around there. Because they were about the same distance, the brightest one could be assumed to be the biggest one. What she saw was this direct relationship between stars with a short period, they're not very bright, and then as the stars get brighter and brighter, the number of days it takes for them to change increases. It's a positive correlation. Henrietta Swan Leavitt had just provided astronomers with what they called a standard candle to measure the distance of faraway stars. Now, first time I read that, I didn't know, so the ones that are smaller change faster and the ones that are bigger change slower. Okay, I didn't appreciate what that meant. But her boss, he knew what it meant, and so did all the other astronomers. Astronomers knew that if you use parallax to measure the distance of known stars that have the same time as Leavitt stars, okay, so if they're really quick, they're small. If they're really slow, they're bigger. So use parallax to find our known stars, and then that will reveal the actual brightness of the ones far away. Same cycle time, same actual brightness. And once the actual brightness was known, a faraway star's distance could be calculated using what we call the inverse square law, which personally I think is one of the coolest things. Let's say you take the star you know, right? Then if you're looking at another star and it's 1/4 the brightness, that means it's twice as far away. If it's 3 times as far away, it would be 1/9 as bright, and so on. So as the brightness, as the dimness squares, the distance multiplies. Now, you might not think that's so cool, but I think that the inverse square law is awesome because it works the same for electric charge over a distance. The farther away you get, and gravity too, but okay. I digress. Okay, this is the scientific paper that was released about the news. Henrietta Swan Leavitt was not able to file for a scientific paper because, of course, she was female. But her boss filed for it, and you'll notice there's no name. It has the circulation number that her boss acquired, but he didn't put any name on it at all. As a matter of fact, in the first paragraph, he said, the following statement regarding the periods of 25 variable stars in the small Magellanic Cloud has been prepared by Miss Leavitt. So he gave her total credit for it too, and that's why he's one of my heroes, besides all these remarkable women. Leavitt's technique launched an entirely new understanding of the universe. Using Leavitt's law, astronomers learned that the Milky Way is not the entire universe. They used to think it was. They used to think that the galaxies that we see that look like dust clouds, they used to think that they were dust clouds within the Milky Way and not faraway galaxies that could be even larger than the Milky Way. Edwin Hubble used Leavitt's technique to determine that the universe is expanding. And we can now measure up to 20 million light years away. And we're still learning. Leavitt lived long enough to learn that the small Magellanic Cloud is 200,000 light years away. This is the small Magellanic Cloud. And this is the large one, which is actually closer at 158,000 light years. Pretty far though. And this right here, this really bright thing, that's 47 Tucane. It's a globular cluster, and it's only 13,000 light years away. But before Leavitt, we would not have known any of that. She died in 1921, and here is a picture of her taken that same year, looking through a telescope. Boom. And of course, I had to tell you about Marie Skłodowska-Curie. And the name of this story is Sometimes Heavy Lifting is Involved. Now, I try not to tell too much about a person's personal life. I want to talk just about their science, but Skłodowska, this little 10-year-old, faced unbelievable challenges. She lived in Poland, and Poland had been partitioned by the Russian Empire at that time. So she had to learn how to speak Russian in order to go to elementary school. Then her mother and her sister both died within 3 years of each other. She and her sister Branya and Catherine lived with their father. Helena lived with their father, and girls were not allowed to have higher education. So they attended an illegal flying university. The Polish parents in the neighborhood took turns in their homes, homeschooling the girls. They called it flying because it would go from one house to the other because it was illegal. If they got caught, they'd be in big trouble. And it's hard to believe today that that would be true, but it really was. And then I have to include this story too because it's such a great sisterhood story. When Maria, this is her here on the left, was 24, she and her sister Branya went to Paris to attend the Sorbonne University because it was the only university in all of Europe that would take women. So of course now they had to learn to speak French in order to go to the university. And when Branya went to school, Maria took a job as a governess and paid for Branya's tuition, and then once Branya graduated, she returned the favor and paid Maria's tuition. while she was in Paris, we all know the story, she met Pierre Curie, who was a professor at the Sorbonne, and he invented an electrometer that could detect small electrical changes. And when Maria and Pierre married, that's when she took his last name. And she changed Maria to the French form, Marie, and she became Marie Curie. In 1903, their friend, Henri Becquerel, he saw something strange with uranium salts that he couldn't explain. Yeah, he had a jar of uranium salts. He put them in his desk drawer in the dark with some film. And then a few days later, when he developed the film, he noticed the film was exposed. So he's like, what the heck? He thought maybe it had something to do with the fact that it glows in the dark, that uranium salts glow in the dark. So he's testing other things that glow in the dark. Anyway, he couldn't figure it out. So he called on his friends Marie and Pierre and to study this strange energy. And it was Marie who determined that the energy was actually radioactive decay, and she coined the word radioactivity. The three friends won a Nobel Prize for Physics in 1903. Okay, so the story goes on. Marie and Pierre, they want to continue studying radioactivity, but they don't have any uranium salts. So they got an idea. All right, we'll get this pitch blende rock that has uranium in it, and it also contains bismuth, barium, and all this other stuff. And we'll remove the uranium ourselves. That's when Marie noticed, hey, wait a minute, there's more radioactivity. She used Pierre's electrometer to test how much activity there was, and she said, wait a minute, there's more radioactivity in this pitch blende than there is in uranium. So there must be something else hiding in here. There must be something else that's radioactive. So I'm going to name it after my country, polonium. And the search for polonium was on. Forget doing any more research with the uranium. They wanted to find this unknown substance. So they reasoned that a good way to find this polonium would be to break down the pitch blende in a known way. And they followed the directions for removing bismuth. Now you might know what bismuth is. It's the stuff in the antacids, Pepto-Bismol. All right, it's an element. So they reasoned that maybe if they just followed the directions, they would at least tell them how to break down the rock. Well, they got bismuth all right, but the weight and the spectrum of their sample showed that it was not pure, and it was radioactive. So they found polonium. So, of course, women were not allowed to present to the scientific community. So Pierre acted as Marie's representative, and he showed the Academy Marie's impure sample of bismuth. And they're like, okay, we'll accept that this impurity is another element, and we'll let you call it polonium. All right. And he's like, well, meanwhile, now that you guys are here, I gotta tell you that my wife thinks there might be another radioactive substance in the pitch blende, too. Because the energy in uranium plus the energy of the polonium did not equal what was in the pitch blende. There was still something else hiding in there. So the Academy said, okay, this time you need to isolate, you need to get a piece of this. You can't just give me an impure sample of something. You have to actually show us. So the Curies set to work again, this time in search of an element they called radium. They were not wealthy, the Curies. But they got an old drafty leaky biology shed that the university said they could use. And pitch blende was expensive. Of course, because it had uranium in it, it's expensive. So Marie contacted the production mine where they took the uranium out of the pitch blend, and she said, hey, do you have any leftovers? You know, like after you take the uranium out, can I get the rest of the pitch blend? And it turned out that they were just dumping the depleted pitch blend in a forest nearby. Can you imagine the EPA today? Oh my gosh. But they had no idea, right? So the company said, sure, you can have all of this depleted uranium, this depleted pitch blend that you want. You just have to pay for somebody to pick it up and deliver it. And that's what they delivered it in, a quarry cart pulled by a horse like that. So they brought this truckload of rocks to their leaky lab. Marie and Pierre are often shown like this, but in actuality, their job looked more like this. Marie wrote, sometimes I had to spend a whole day stirring a boiling mass with a heavy iron rod nearly as big as myself. I would be broken with fatigue at day's end. She also, however, wrote that it was one of the best times of her life because she was so excited about what they might find. The smell, just imagine for a minute, okay? The smell of the melting metal and the burning wood, the bubbling acid, and the students stayed away from that biology shed that they were using for a lab. And sweat and dirt were the norm, but like I said, Marie thought it was really exciting. The Curies first broke the rock down manually, and then they broke it further by using acids or bases. And then they separated the solids from the liquid, kind of the way you would, pour pasta into the colander, and separate it. And then they'd have the liquid and the solid, and they used Pierre's electrometer to see if the energy was then in the solid or in the liquid. Finding the energy was still in the solid portion, they discarded the liquid and broke the rock down even more. And they kept going through this, breaking rock and straining out the liquid until they found that the energy was in the liquid. At this point, the liquid glowed green. They had jars of it around their lab, and she said it was like night lights. And all they had to find was 1/10 of a gram of radium, which is like about as much of a few grains of rice. So they dried out the liquid that glowed green, and they collected the dust that was left behind. And like I said, this labor-intensive job went on for years. And Marie had to finish on her own because Pierre died. He was killed while crossing a street. Now they said that he was hit by a horse and buggy going down the street, but the fact is it came to light that he had actually fallen and then got hit by the horse. So they believed that he had been suffering from radiation poisoning when he died. Overall, I'm going to read this word for word because I don't want to get it wrong. The Curies processed 8 tons of the rock called pitch blend, and they used thousands of gallons of water to extract the necessary 1/10 of a gram of radium. But they did it. Marie Skłodowska-Curie got the Nobel Prize in Chemistry for discovering polonium and radium in 1911. She was the first woman to win a Nobel. She's one of only 4 people to this day to ever win 2 Nobels. And she is the only person ever awarded 2 Nobels in 2 different categories. The first one was in physics for discovering radioactivity, remember with their friend Henri? And then the second was in chemistry for discovering the 2 new elements. In 1961, the International Astronomical Union named a crater on the moon Skłodowska in her honor. She died in July of 1934, and she died of aplastic anemia, radiation poisoning. And the next year, 1935, just as an aside, her daughter won the Nobel in chemistry. Okay, the next lady I'd like to tell you about is Mary Fairfax Somerville. Anybody ever heard of her? Okay. She dreamed of going to school. She grew up on Burnt Island in Scotland in the 1780s. She couldn't go to school, but she learned to sew and play the piano and read the Bible, because that's what ladies did. But all she ever wanted to do, and I mean her whole life, all she ever wanted to do was go to school. From learning to read the Bible, she taught herself to read everything, and she read everything she could get her hands on. She read everything in her father's library. She stayed up late at night reading by candlelight because her father forbid her from reading, because he honestly feared that reading would addle her female brain. Imagine. She married and her husband died young, leaving her with 2 children and a small inheritance. Mary and the children moved back with their parents, and of course, she used the money to buy books. And she wrote letters to a professor at a neighboring university and exchanged math problems and solutions by mail. So that's how she learned how to do mathematics. Yeah, she was determined, but she always wanted to go to school. During her time, all of the science books were written in French. Remember, the Sorbonne, too, in France was the only place that accepted women. France was the center for science. But Mary wanted to learn science, too. So she, with the help of an English-French dictionary, she read science texts, including Traité de mécanique céleste by Pierre-Simon Laplace. At age 32, Mary married again, this time to Dr. Somerville. He was a physician and a member of the Royal Society. Now that doesn't mean that he's royal, it means it's the United Kingdom's Academy of Science. So he was a scientist and a physician. And he absolutely loved that he found a woman who was interested in science. They did all kinds of science things together. They collected fossils and looked at stars, and they had this whole science life, right? And then one evening, Mary Somerville was seated next to Laplace at one of those Royal Society gatherings that her husband would go to. Laplace, remember, is the man who wrote that book that she read using a French-English dictionary. She was so embarrassed. She didn't know how to speak French. She could only read it, so every word was phonetically sounded out in her Scottish accent. Oh my God, she was so embarrassed. But he was charmed. He loved that this woman was sitting next to him talking about his book. And so time went on, and the Somervilles lived in London flat and had more children. She taught them all math and science, but she hired a tutor so they would never be embarrassed like she was with the languages. And just an aside, Mary Somerville taught Ada Lovelace, who became a famous mathematician in her own right. And then in March 1827, something unexpected happened. Somerville got a letter from Lord Brougham of the British Parliament asking her to translate Laplace's work. And she's like, I don't think I could do it. You gotta find somebody else. I never even went to school. I can't translate his book. But with some urging from the Parliament guy and her husband, she said, okay, I'll do it, but you have to be quiet, because if it doesn't turn out, I don't ever want anybody to know about it, right? Well, it turned out that Brougham came to her because he first went to Laplace and said, we need your book translated into English. And Laplace said, well, you have a subject right there in Scotland. You know, she lives in London. She can do it. So anyway, she had another request. Not only was it to be kept silent, but she said, if I'm going to translate the words in his book, I have to explain the mathematics as well. So I said, okay, do whatever you got to do. And 4 years later, she published her multi-volume translation, Mechanism of the Heavens, and that's one excerpt page where she included not only the English translation, but what it meant. Mary Somerville single-handedly brought science to the entire English-speaking world with that book. And a few years after that, at 40 years of age, she published her own book, The Connection of the Physical Sciences. She made connections between all the different sciences, like astronomy connects to chemistry and math and geology. She made connections, and that was never done before. Scientists were either geologists or mathematicians or astronomers. She combined it all together. And in a review of her book, the word scientist was coined for the very first time to describe Mary Somerville. When she died, her obituary called her the Queen of Science. Okay, and the last lady I want to tell you about is a woman named Eunice Foote. In 1856, Eunice Foote demonstrated the greenhouse effect in her home laboratory. She was interested in geology, and she learned that during the Carboniferous period, there was more CO2 in the atmosphere. And so she wondered how that was different. You know, the Carboniferous, you know, it's got the word carbon in there, that's when carbon was being created, forming in the swamps. And she learned there was more CO2. So she did the experiment. You can do it yourself if you want. She took 3 jars and put thermometers in each, moist air in one, dry air in the other, and the high concentration of CO2 in the other. You can do that by just breathing. And then she placed the jars in the sun. And she found that the moist air heated more than the dry, and she found that the sun had a much greater effect on the cylinder containing carbon dioxide. She found what we call statistically significant results. She wrote, the receiver containing the gas became itself much heated, very sensibly more than the others, and on being removed from sunlight, it was many times as long in cooling. So her conclusion was that more CO2 in the air results in a warmer planet. Therefore, Earth of the past, when CO2 levels were higher, must have been warmer. And of course, she couldn't present her own paper because she was female, but she depended on her friend Joseph Henry, and he presented her paper at a meeting of AAAS, American Association of the Advancement of Science. And that's her paper. Eunice Foote made a discovery in 1856 that should have informed humans how to proceed into the future. More than 50 years later, in 1912, there was this article in Popular Mechanics that said the furnaces of the world are now burning 2 million tons of coal a year. When it's burned and the carbon unites with oxygen, it adds 7 million tons of carbon dioxide to the atmosphere annually. This tends to make the air a more effective blanket for the Earth and raise its temperature. And he said the effect may be considerable in a few centuries. Nothing to worry about, right? But then in 1938, this meteorologist named Callendar, he said, no, not a couple of centuries. They estimated that the temperature would go up 0.003 degrees Celsius per year, and he calculated, now this is back in 1938, when they didn't have nearly as many cars or airplanes, or you're putting a lot more CO2. He said that the temperature at that time in 1938 was raising instead at an average of 0.005 degrees Celsius per year. Then I quoted this from AAAS. They said on the 5th of November, 1965, okay, now 100 years have passed since Eunice Foote. 1965, the group known as the President's Council of Advisors on Science and Technology cautioned President Lyndon Baines Johnson that continued accumulation of carbon dioxide, atmospheric CO2, resulting from fossil fuel burning would almost certainly cause significant changes and could be deleterious from the point of view of human beings. Now, if you don't know the word deleterious, let me tell you, it's got the word delete in there. Okay? What it means is there could be unexpected, unprecedented changes. Then in 1977, this little article, let's say it's July 1977, this little article appeared in the San Francisco Chronicle that says, it's called Warning on Change in World's Climate. It's kind of blurry, but what it says is the temperature rise could have adverse, perhaps even catastrophic effects around the world. And they used the word greenhouse effect. 1977, how long ago was that? Yeah. Eunice Foote died in 1888, and she had no idea of the importance of her discovery. Some people still don't think it's important. Any questions about Nightingale Levitt, Curious in the World? Any slides you'd like to see?